So let's consider the G, which is a function of temperature, pressure, N1, N2 to Nc. Let's differentiate both sides. So dg is equal to, let us be right, dg is equal to dou g upon dou t, keeping pressure, and Ni dt plus dou g upon dou p dp, where temperature Ni plus sigma of dou g upon dou Ni, where I is equal to 1 to C, where temperature, pressure, Nj, where J is not equal to I, dni. So any system which is where we measure the G is a function of temperature, pressure and number of components, and if the system is isolated where no exchange in temperature and no exchange in means no change in pressure is occurring, as well as the number of component is also constant. But let's divide that system in two parts, and in that system also both phases were existing, that is the liquid phase and vapor phase. So such cases, because it is isolated, there is no change in temperature, no change in pressure, or we consider it is constant temperature and constant pressure. Okay, consider it constant temperature and constant pressure. The term can be written dg is equal to 0, because I have considered that in the system is isolated, there is no change of component is also there. So that moment this all is going to work. But we divide the system in two parts, two subsystem A and subsystem B, as I just told. So that case temperature and pressure will be constant, but the number of components, change in number of components with respect to subsystem will be exist. So the dg is equal to dg of A plus dg of B, and this will be 0. So if you look at from here at subsystem, we also talk about the subsystem. So at subsystem, T and P are constant, because in subsystem the change in number of moles in subsystem A is taking place, as well as also in B is taking place. So that moment from the equation this we can write dg is equal to sigma of I is equal to 1 to C. This is what dou g upon dou ni. This we have dou g upon dou ni, can write mu I. So let's write mu I and dni. Okay, dni. So for subsystem A, for subsystem A and B, dou g A will be sigma of I is equal to 1 to C mu I dni A, and dou g B is equal to sigma of I is equal to 1 to C, here mu I A and mu I B dni B. Let's put these two over in this equation and check. So I is equal to 1 to C mu I A dni A plus sigma of I is equal to 1 to C mu I B dni B is equal to 0. As we know that the system Ni, component Ni in the overall system is a summation of component I in subsystem A plus component I in subsystem B, and let's differentiate both sides. So because that system is closed, isolated, there is no exchange of components between the system and surrounding, this become 0, like we have considered over here. So that moment the dNIA is equal to minus dNIB, or dNIB is equal to minus dNIA. So let's put this value over above equation and see what happening. So dNIA plus I is equal to 1 to C mu IB, now minus dNIA is equal to 0. So both dNIs were there. So I is equal to 1 to C mu IA minus mu IB is equal to dNIA is equal to 0, or mu IA minus mu IB is equal to 0, or mu IA is equal to mu IB. So it's mean that in any system where temperature and pressure were constant, so in between two phases, the chemical potential of component A is equal to the chemical potential of component I in subsystem A is equal to the chemical potential of component I in subsystem B are equilibrium. And we can say that there is no changes is taking place, or even we can say that there are no reaction is taking place in such conditions. Just now we saw the uh, equality of chemical potential between the two subsystems. Now let's see the effect of temperature and pressure over the chemical potential. So effect of temperature and pressure over chemical potential. So dou mu I by dou T, keeping pressure and Ni constant, is equal to dou by dou T and dou G by dou Ni, here temperature, pressure Nj, and here pressure Ni. So in denominator is there, so let's rearrange, or we can write dou G by dou Ni and dou T. Just we have rearranged, and we also know that dg is equal to minus sdt plus vdp. So let's divide dt in both sides, and because here we keep pressure at the outer, so the pressure in this case pressure and, or better we keep in the inner side and write this dou by this. Just I will rearrange dou by dou Ni into dou G by dou T. So here pressure and Ni will be constant, and here temperature and pressure and Nj, where J is not equal to I. So this case dou G by dou T Pni, this term keeping pressure constant, and here keeping pressure constant, here pressure and Ni constant. So this term goes to 1 and this term goes to 0, and this I write St, where St is the entropy, total entropy. So now dou G by dou T with P and Ni, we can write St, so that dou mu I by dou T P Ni is equal to dou by dou Ni St, where temperature, pressure and Nj, where J is not equal to I, and dou St by dou Ni we can write Si bar, partial molar entropy. So the change in chemical potential with respect to temperature is considered as change as the partial molar entropy. Similar way, let's see the effect of pressure. So let's take mu I dou by dou P, and that moment temperature and Ni will be there. So that dou upon dou P, dou G upon dou Ni, temperature, pressure Nj is not equal to I here, and here temperature and Ni. So we refer same procedure here. We know that the dg is equal to minus sdt plus vdp. So here T I am representing total entropy, total volume and total Gibbs energy. So what we need, we rearrange this. So dou G upon dou Ni and dou G upon dou P, where T and I, and here temperature, pressure and J. So what I need dou G upon dou P. So let's divide dP and keeping temperature and Ni constant. So that moment this term goes to 0 and this term goes to 1. So this is comes Vt. So let's put over here. So dou mu I by dou P T Ni is equal to dou upon dou P, dou Ni. So Ni will become here Vt, where temperature, pressure and J, and this is written partial molar volume. So the change in pressure in chemical potential with the come out with the partial molar volume. So we can see here the effect of temperature is comes with the change in the partial molar entropy, and the effect of pressure over chemical potential will be counted as partial molar volume. So these are the effect of temperature and pressure over the chemical potential. Now we will see the fugacity and fugacity coefficient. So mu I is equal to dou G upon dou Ni T, P and J, where J is not equal to I, and this is represented by Gi bar as we have seen from the last class. So we know that Gibbs Duhem relation. The relation was sigma of Ni dgi bar plus sdt minus vdp is equal to 0. So let's put the value of gi bar as a mu I. So we can write di mu I, ni mu I d mu I plus sdt minus vdp is equal to 0. So this relation as a Gibbs-Duhem relation in the form of chemical potential. Let's say the condition where temperature and pressure were constant. So at constant temperature and pressure, when constant temperature and pressure, these two terms become 0, and we can write sigma of Ni du mu I is equal to 0. This is the relation. This is the relation where we can see with the multiplication of number of components and change in chemical potential, uh, and summation of this all is going to 0, where I is going 1 to C. In all the case, I is going 1 to C. So this is the relation where we can where we use, or the relation which we use for the further calculation of the numerical problems. So mu I is equal to dou G upon dou Ni T, P and J, where J is not equal to I, and this is represented by Gi bar as we have seen from the last class. So we know that Gibbs Duhem relation. The relation was sigma of Ni dgi bar plus sdt minus vdp is equal to 0. So let's put the value of gi bar as a mu I. So we can write di mu I, ni mu I d mu I plus sdt minus VdP is equal to 0. So this relation has a Gibbsian relation in the form of chemical potential. Let's say the condition where temperature and pressure were constant. So at constant temperature and pressure, when constant temperature and pressure, these two terms become 0, and we can write sigma of Ni du mu I is equal to 0. This is the relation. This is the relation where we can see with the multiplication of number of components and change in chemical potential, uh, and summation of this all is going to 0, where I is going 1 to C. In all the case, I is going 1 to C. So this is the relation where we can where we use, or the relation which we use for the further calculation of the numerical problems.